Assalamu alaikum. Now, this is in continuation with the previous lecture concerning the compensation and controllers. Now, in the last lecture, we were given a unity feedback system with an open loop transfer function. We plotted the root locus and found out that that system actually has a root locus such that it was going towards instability. Now, by adding a simple 0, which is located at the origin, the root locus was modified in such a way that the system was always stable, and moreover, there was a shift of the entire root locus towards the left, that is making the transient response much better, that is speedy in terms of getting rid of the disturbances. Now let's take up example 3 in fact. And example 3 is we are given an open loop transfer function of a system which is k s plus 1 s plus 3. Now this is basically a second order system. Now we all know that second order system is always stable. Now let's plot the root locus in fact. So the poles are located at -1 and -3. There is no physical 0, however there are 2 at infinity. There are 2 zeros lying at infinity. Now the next is the p minus z. So the number of poles are 2. There is no physical 0, so p minus z is equal to 2. And of course the number of loci are equal to the number of open loop poles, which are 2 in fact, so the number of loci is equal to 2. Now let's plot the poles, open loop poles. One is at -1, the other is at -3. Now comes the question of the real axis loci. Now there is no 0 in fact, so eventually we have 2 immediate adjacent open loop poles. So there is a real axis loci which is lying between these 2. So the real axis loci is between -1 and -3. Now this means that we must have one breakaway point. Now in order to find out the breakaway point, we use the angle magnitude criteria. In fact, this is KGSHS, and again the system is a unity feedback system for which HS is equal to 1. So angle magnitude criteria is this one. So if we put this over here, we will have s square plus 4s plus 3 by multiplying the factors. This is equal to -1, and then k is equal to minus s square plus 4s plus 3. So we have dk by ds, the next step, and we have minus d by ds of this entire function. So this is then equated to 0, and when we take the derivative, we will have 2s plus 4 equal to 0, or we will have s is equal to -2. So this means the breakaway point is sigma b is equal to -2. So this one is the breakaway point. This is sigma b. Now once we have the breakaway point, we must look at finding the center of asymptotes and then the angle of asymptotes. We use that formula for the center of asymptotes. Sigma c is equal to sigma c is equal to big sigma p minus big sigma z divided by p minus z. So we have -1, -3, no zeros, and then we have this 2, so we have again this is equal to minus 2. So the same point is our sigma c as well. This is the center of asymptotes, and to remind you that about the angles of asymptotes, we have the formula which is 180 into 2m plus 1 divided by p minus z. And if you work for m is equal to 0 and 1, we find that the angles are 90 degrees and 270 degrees. And remember, no more angles because p minus z is equal to 2, so we must have two angles for asymptotes, one 90 degrees, the other 270 degrees, and it should be drawn at the center of asymptotes. So these are the asymptotes, one at 90 degrees and the other at 270 degrees or minus 90 degrees. Now the the root locus will take off from this breakaway point, which is this one, and it will move in search of their zeros at infinity, where the gain is infinity. So this is the open loop pole, this is the open loop pole where the gains are 0, and it's looking for the two zeros which are lying at infinity. In fact, this transfer function, which is a second order system, is always stable. The reason is that the root locus is simply a vertical straight line, and it's not in any way going into the right half of the S-plane, which is an unstable region. So we can say the system is always stable. However, let's do a little modification with this system. And in the previous case, we have incorporated a 0 at the origin. Now, in this very case, we will incorporate a pole at the origin. A simple pole at the origin, that is having a transfer function 1 over s. So this means we will modify the function which now becomes this one. This is the original system. Now this is the modified system. So the modified system is simply resulting from something like incorporating a simple open loop pole at the origin. So in this case, the number of poles are 0, their values are 0, minus 1 and minus 3. Whereas there is no physical 0, however there are 3 at infinity. Now there are the p minus z. This is important. P, the number of poles are 3, there is no physical 0, so we have p minus z is equal to 3. And the number of loci is equal to the number of open loop poles, which is equal to 3 in this case. Now let's have the plotting of the poles on the S-plane, in the S-plane, and then we will draw the root locus. Now let's plot the poles. We have a pole at the origin, we have a pole at minus 1, and then we have a pole at minus 3. Now let's have the real axis loci. Now this is where the real axis loci will be, that is between 0 and minus 1. So the real axis loci is between 0 and minus 1. That is two immediate adjacent zeros looking from this side towards the left. So we have two, starting from this one, there is an immediate adjacent open loop pole. So there is a real axis loci which must lie between those two. And then we have a real axis loci which is lying between this open loop pole and an open loop 0 which is lying at infinity. So we have a real axis loci between 0 and -1, and then we have a real axis loci between -3 and tending towards -infinity in search of x0 lying at infinity. Now once we have done that, now we are expecting one breakaway point over here, because there is a real axis loci which is lying between two open loop poles, immediate open loop poles. So let's find out, and the breakaway point is found out by again using the angle magnitude criteria. So in fact we can say that K is equal to minus S into S square plus 4S plus 3, or which is equal to minus S cube plus 4S square plus 3. So if we take the derivative with respect to S, then this is equal to 3S square plus 8S plus 3. And when we equate this to 0, we will get an equation which is a quadratic equation, and this is 3S square plus 8S plus 3 equals 0. This is the quadratic equation which will give you two roots, and amongst the two roots, one root will be the breakaway point. So in this case, the breakaway point is at minus, S is equal to minus 0.41, because the other one root, if you work out, it is something like 2.21. So 2.21 is not lying on the real axis loci. However, this minus 0.45 is the breakaway point which is actually lying between the real axis loci, that is somewhere over here, and this is where it should be approximately. So this is our breakaway point. Now once we have the breakaway point, then we must look for the center and angles of asymptotes. Now the center of asymptotes is worked out as such. So we have -1, 0 of course anyhow, doesn't make any difference in this case. This is, so we have -4 over 3, which is equal to -1.33. Now this means the center of asymptote is 1.33. So we have a center which is -1.33 is somewhere over here. So this is, now let's look for the angles. Again, the same usual formula. For n is equal to 0, 1, 2, 3, etc. So for n is equal to 0, it will be 60 degrees. If you work out accordingly, for n is equal to 1, this will be 180 degrees, and for n is equal to 2, it will come out to be 300 degrees. And then for m is equal to 3, it will again come 60, so there is a repetition. So since the number of angles must be equal to p minus z difference, which is 3 in this case, so we have 3 angles, 60, 180 and 300. Now if we draw these angles, so this one is 60, this one is 180, and then this one is 300. So we have 3 angles for asymptotes, and we can draw the asymptotes according, selecting the center which we have, and then the angles. Now once we have done that, now we are in a position to draw the root locus, but then we must look for the j omega crossing point, because in this case the asymptotes says that the root locus will be guided in such a way so that it should then cross this j omega. Now for that purpose we need a closed loop transfer function of this open loop transfer function given to us. The system is a unity feedback system, So the closed loop transfer function according to the formula will be GS KGS, okay, just put it like this if you want to, KGS HS, and HS is equal to 1 anyhow, so the transfer function will be S square plus 4S plus 3 plus K, or K divided by S cube plus 4 S square plus 3S plus K. Now this is the closed loop transfer function. The characteristic polynomial is the denominator, which is Qs is equal to S cube plus 4 S square plus 3S plus K. Now likewise we go for changing S to J omega, and if you put J omega in this equation, we will have minus omega cube minus 4 omega square plus J 3 omega plus K, and when we equate this to 0, we will get a characteristic equation in terms of its Fourier transform, or in terms of the J omega when we transform S to J omega. Now if we connect the imaginary terms together, so if we collect the imaginary terms, we will get omega minus J omega cube plus J 3 omega equal 0. So we will have omega square is equal to 3. So this one is then equal to, when we get rid of one of the omegas and transform this to other side, this is omega 3, which is omega is equal to under root 3, which will give us omega is equal to plus minus 1.732. Under root 3 is very familiar in electrical engineering, so it's easy, 1.732. Now incorporating J with both sides, that is multiplying with J. So the J omega crossing point, J omega crossing points are plus J 1.732 and minus J 1.732. So this means we have 1.732 is somewhere over here and minus over here. So now it's easy. We simply draw a smooth curve which must pass through this and is guided along the asymptotes. In search for their zeros lying at infinity. Now compare this root locus with that of example 3. The one which we have a system which does not actually have S, which was this one. Now that was a straight vertical line and it was a stable system, all-rounder stable system. But then when we have incorporated a simple open loop pole at the origin, now the scenario completely changed. Now just have a look at this diagram. Number one, the root locus says that the system is going in the unstable region. So you must be careful in choosing the operating point. And then secondly, it is shifted towards the right. If you have a look at the previous root locus, that was more towards the left. You can ascertain this from the breakaway points. The breakaway points in the previous case was minus 2. And in this case, it is minus 0.45. So there is a shift. It means the entire root locus is shifted towards the right. Now this means the transient response is deteriorated. It is disturbed. The transient response is such that the system becomes a rather slow in getting rid of the transient or disturbances. And secondly, if you look, the system is going in the unstable region. So what we have done actually is simply adding a pole at the origin. Now it has twofold effect. The first one is the entire root locus is shifted towards the right. That is, the transient response, which was something like this, if we expect in the previous case. Now it would be something like this, that is a longer duration transients. This means the disturbance will not die out quickly. It is slow system, slow acting system in terms of rejecting the disturbances. And secondly, it is going in the unstable region after some time. For example, if you keep on increasing the gain. If you increase the gain, eventually the system is going towards instability. So this is the optimum point. Afterwards, the system becomes unstable, and you must work in choosing operating system somewhere over here so that there is an adequate gain margin as well. Not right at the j omega axis, near the j omega axis. You must be a little further from the j omega axis towards the left, such that the system should have adequate gain margin incorporated. So anyhow, the conclusion is that if we consider this one as a controller, that is K over S, and the original plant is then 1 over S plus 1, S plus 3. So with the original plant, all we have done is to incorporate an integral controller. This is an integral controller because 1 over S is integral basically, S is the derivative. So this is a simple gain integration we are performing on the system, on the plant, and that leads the system to have a root locus which is now as such shifted towards the right and then going into the unstable region. In fact, we have deteriorated the system's performance. So adding or incorporating a derivative control will improve the transient response. If you incorporate integral control, it will deteriorate the transient performance. Now, something good about integral control as well. Now, when we shift the system root locus towards the right, actually we are increasing the gain. We are then incorporating more gain into the system. This means the steady state response will improve. So, what happens in this case? The steady state performance is improved by some sort of deterioration in the transient response component. Anyhow, if you like it, that's okay. If you don't like it, then you have to revert back to the derivative control. So, in fact, a derivative controller or a derivative control actually puts the system right according to the proper transient response, and then the incorporation of an integral controller would actually make the system gain increase to improve the steady state. However, it will at the expense of deterioration of the transient response. So let's conclude something, and the conclusion is very simple. If we add or incorporate a derivative controller, this will improve the transient response, that is shifting the root locus towards the left. So it means the system will become more speedy in rejecting the transient or disturbances. Now, on the other hand, when you incorporate an integral controller, a simple gain integral controller of the form K over S, then you are actually deteriorating the transient behavior of the system in terms of slower acting system in getting rid of the disturbances. But you are actually modifying or putting right on the right track the steady state response. You are improving the steady state response. However, one thing you must note over here, and it is worth mentioning, that pure derivative, simple gain, pure derivative controller and simple gain, pure integral controller are not practically available. Practically, we have proportional controller. That is, we have proportional derivative controller. Which is called PD, proportional derivative, and the transfer function is something like SKD plus K. Then we have instead of pure gain integrator or integral controller, we have proportional integral controller. The transfer function Pi, this is Pi designated. The transfer function is Ki over S plus K. Now this means a proportional gain in both cases is incorporated, so that is why they are called proportional derivative and proportional integral controller. Now the combination of the two will actually modify both the responses, transient as well as steady state, that is they will improve transient response as well and steady state response, and they are then referred to as PID controller. Proportional integral derivative controller, and the transfer function is SKD plus Ki over S plus K. Or you can put this figure over here and then, so never mind. So we have three types of controller. PD improves the transient, it compensates the transient response. This is for compensation of the steady state response, PI controller, proportional integral. Now this is for the compensation of both, that is PID controller, proportional integral derivative, and proportion means adding a proportional gain in either case. So practically we have PD, PI and PID controller. Now the last important thing, if you look into the system transfer function, that is the original system was this one, the second order system. Now this is basically type 0 system. Now by incorporating a simple integration in the forward path, this one. Now this is now type 1 system. Now this means that the number of integrators you are using actually increases the type order. So if you use 2 integrators, then this becomes what is called type 2 system. So we have type 0 with no integration in the forward path. Type 1 we have a single integration in the forward path. Type 2 when we have double integration or 2 integrations in the forward path. So the number of integration in the forward path actually governs the system type. So in this case what we have done is we are actually have changed the system type from type 0 to type 1. That is the steady state performance is improved. But then the order of the system also is then becoming a third order. So third order systems are not really all the way stable. Second order system theoretically are all stable systems. So anyhow, this is today's lecture, and we have finished with compensation, and we have described the controllers by quoting 4 examples. Example 1, example 2, example 3 and example 4. Please, dear students, go through these examples and accompanying handouts. And if there are any questions, inshallah, we will have a session, an interactive session. But please do work hard, because unless you work hard yourself, you won't be coming up with reasonable questions. Thank you very much. Allah ku salamat rakhe.